Thank you very much for this award, and building off of the description of your how you described how awarding this award is quite important. I think I can make a praise of praise or a type of meta praise of awards briefly, because this morning I happened to be reading this book. Perhaps you can see it. And I came across this passage, which is really relevant. And so the author, David Brooks, writes that there is something in being seen that brings forth growth. If you beam the light of your attention on me, I blossom. If you see great potential in me, I will probably come to see great potential in myself. And so usually we think of these awards as acknowledging past work, but I think there's also a way that these type of awards can encourage future groundbreaking work. And that's what I hope, at least. And so part of the reason why I'm getting all these awards year by year is in no small part due to the work of Francois Renard, my postdoc advisor and now mentor and collaborator. And I really can't say enough nice things about Francois, but he's really an excellent mentor and just a great person as well. And I can summarize all of his attributes by giving a recommendation. So if you're a student looking for a postdoc or a PhD project, then I recommend to search out Francois. And then another person who has been so important in the work I've done at ESRF and so really in the building of my career is Ben Cordinaire, who's the ESRF beamline scientist that is responsible for, I think, all of the experiments that I've worked on at ESRF. And it's really astounding the different variety of skills that he has a deep knowledge of. And so from setting up the equipment on the beamline to building the equipment and the specific apparatus that we need to do our experiments, to post-processing the data and applying machine learning to pick out the parts of the data that we want to analyze. It's really, he's really integral to my work at ESRF. And then Yehuda Ben Zion has been very important in this process too, because he helps us understand how to link the observations that we make in the laboratory to crustal systems. And so the broad process that we study at ESRF is illustrated in this schematic figure, which is the deformation of rock surrounding a fault zone that slips in an earthquake. And so because we saw from the poster session, as well as I understand my parents could be in the audience on Zoom, I included a few slides so we get onto the same page. So in this conceptualization of an earthquake, in the simplest understanding, we can think of an earthquake happening on a fault as with the block and slider model. So there's some tectonic force that's pushing or pulling the system, which is some block. And so when the force along the fault is large enough to overcome the strength of the fault, then an earthquake will happen. And this is called a stick-slip instability and looks something like this with the tectonic force acting on the block. And so in this model, we have this very localized fault plane on which the earthquake happens. And the earthquake occurs instantaneously. But in reality, it looks more like this in the crust, where we have some brecciated zone of highly damaged rocks inside of fault core, which is a volumetric or a volume of rock. And then outside of that, the host rock is not this pristine block, but is consists of many fractures and is heavily damaged. And we can see this by looking at faults in the field. So with increasing distance from this fault core, we can count the number of fractures in the host rock and see that the density of fractures is related to where the fault is, but that it's not this pristine material. And so the other notion with this block slider model of earthquakes, the stick slip instability that we have to reconsider is that the earthquake does not occur instantaneously when the stress on the fault is large enough to overcome the strength of the fault. And instead, there may be a precursory state where we can recognize when a large earthquake will happen. And so in the laboratory, we can see this, that when you start to slip on a fault, first you can slip relatively slowly, and then over some distance, after some amount of slip, the slip begins to occur much more quickly. So this could be called the nucleation phase. And so this type of nucleation phase fits within the earthquake cycle in this way, in that over hundreds or thousands of years, you have this long-term interseismic loading of the crust in which the fault can stay relatively locked and not slip. But then at a certain point, some slow slip can begin on the fault, and then in this nucleation phase. And then after that, there's this very much faster coseismic slip phase. And so one of the type of precursors that we can observe in the field is related to water levels measured in wells. And so fracture propagation and opening, as well as fracture closing, can change the level of water in wells. And so this effect is demonstrated nicely after the Northridge earthquake. And so in this earthquake, it produced this region of the crust that contracted. And so in this region, the water level in the well increased. So you close the fractures and then increase the amount of water level. And then in this other area of the crust, the rock volume extended, and then it decreased the level of water in the crust. But you notice that these signals are generally after the earthquake, and there's less clear evidence following preceding earthquakes. But a much more common precursor than changes in the water levels are more commonly observed are these types of smaller earthquakes that are called foreshocks. And at least before this paper, it was thought that less than half of large earthquakes were preceded by foreshocks. But this could be related to the completeness of our earthquake catalogs, or how sensitive they are, how many earthquakes they're actually detecting. And so at least in this paper, they find that using this more complete record of the earthquakes in Southern California, they find that 72% of the earthquakes with magnitude 4 and above are preceded by foreshocks. And so this is an example of one of these types of foreshock sequences. So in this case, 16 days before the earthquake, the new method of detecting foreshocks identified these smaller red dots, whereas before they only had observed these larger blue dots. And this is how they can see the spatial evolution of these foreshocks. But this is still a debated question in the community for sure. How common are foreshocks to large magnitude earthquakes? And so the phenomenon of precursors related to earthquakes that I focus on at ESRF in particular is this precursory deformation of the rock before a large magnitude earthquake. And so that's the deformation of the host rock outside of this fault zone. And I will say that I could have changed this figure to include a pre-existing fault. So there may be some deformation of the host rock around pre-existing faults before they can slide. And so we'll focus on two questions today. And so the first question related to deformation preceding earthquake rupture is, how does deformation evolve preceding earthquakes? So is it monotonic or non-monotonic in its spatial localization? So does it continually increase in localization, or does it increase and decrease in localization towards catastrophic failure? And then we'll try to answer what geophysical properties are the most useful to track in the crust in order to recognize this precursory phase of the earthquake. And so we've published papers where we consider the characteristics of fractures, such as the length, volume, and orientation And in fact, I won't talk about any of that work today, and I'll only focus on the characteristics of the strain field that may be the most useful to track in the crust. And I'll highlight that, at least I believe that the best way to study this phenomenon is in fact at ESRF on the beamlines ID19 and BM18. And that's because we have methods to subject the rock to confining stress, so representative of some depth within the crust where some earthquakes can occur, and then see inside the rock to see how it's deforming through time, which is really an unparalleled technique to be able to use. So I'm very grateful to be able to do experiments there. And so the first work that we did in this vein was back in 2019, and it was on basalt from the Mount Etna volcano. And so what we do at ESRF, I can be more specific about the methods now, is that we have an X-ray transparent triaxial compression apparatus, so we can put the rock under some confining stress. So it experiences the stress state of some kilometers within the crust. And then we can increase the axial stress acting on the rock in the vertical direction on this figure incrementally, and then take X-ray tomograms after each stress step. So at each black dot here, we have an image of the rock under load. And so without these type of experiments, really the only way to probe what was happening with the fracture network of the rock was to do these types of triaxial compression experiments, but then stop the loading here, for example. If you see my cursor, take the rock out of the rig and examine the fractures that are there. And so that has a host of problems, including the fact that you can form fractures as you take the rock out of the rig, not to mention that it can be incredibly time consuming to do. To repeat this type of experiment, you have to do however many tomograms there are, right? So 50 to 100 individual experiments. So this ability at ESRF has really advanced our knowledge on fracture development and strain localization that happens within rocks at depth. And so in this work, we focused on two experiments done on this type of Mount Etna basalt. And in this case, from the tomograms, we can extract the porosity of the basalt. So this is the initial porosity we find in the tomogram, and then we can track the fracture growth. This is the largest fracture at these different times along the failure path. And so on these loading curves, I will mention that the end of this is catastrophic failure because we load the rock with stress steps. So we have this sudden collapse of the rock after this point, so after the end part of these figures. And so from these tomograms, we can apply a technique called digital volume correlation to calculate the local strain tensors. And so from the three-dimensional local strain tensors, we can extract different components of the strain field, including the contractive strain. So where you have a pore, for example, and then it collapses, as shown in this figure. The dilation of the rock, so when you perhaps have a pre-existing fracture and then it opens, and then I'll show this shear along a fracture. And so what we saw in this work is that we have this failure in Mount Etna basalt occurring first through the localization of the contractive strain, and then the localization of the shear and dilative strain. And so these rough sketches are showing that type of evolution, and what we believe is happening at the pore scale, and what we can see in some tomograms and SEM images afterwards, is that the contraction localization likely occurs through this collapse of pores, and then the shear and dilation localization occurs as these macroscopic scale fractures are coalescing and forming. And these are consistent with observations we have of the Mount Etna volcano from gravity data, which indicate that there's contraction and dilation of the flank of the volcano between these two flank eruptions. So this type of deformation of the volcanic rock is important to understand in the context of recognizing when a volcanic flank eruption can occur. And in this work, we also started quantifying the localization more than just with this qualitative way that I've been using. And so we saw with our statistics that the shear and volumetric strain begin to localize at as early as 50% of the stress at failure, and that's before the macroscopic yielding of the rock recognized in the macroscopic mechanical data. And so following this work, we wanted to see if the localization behavior of the rock was similar in different types of rocks. So we expanded this analysis from the Mount Etna basalt to a sandstone, to as well as low porosity crystalline rocks, this monzonite and granite, to a shale and a limestone as well. And now I'll be more specific in how we characterize localization. So here I'm showing the high magnitudes of the volumetric and deviatoric or shear strain. And these are at 4 different steps of the experiment. And so we can see just qualitatively that the high strain values are relatively diffuse, and then they concentrate themselves with increasing differential stress, so an increasing distance towards failure. And so the way we characterize localization in this case is by calculating the volume of the rock that's occupied by these high strain values. And so we do some discretization because we have this continuous field and we break it into the high strain values. But generally what you should focus on is that as this volume occupied decreases, that's this increasing localization with time. And so in this case, we can see here that the volumetric strain generally increases in localization towards failure, but in fact, there's a phase of delocalization where the strain occupies a larger volume momentarily. And the deviatoric strain experiences some of this behavior as well, we can see in this figure. And so some of the key points from this work is that the vast majority of these experiments did see strain localization towards failure. And in general, the volumetric strain localized to a greater extent than the shear strain. And so that indicates that the dilation could be more useful to track in the crust than the shear strain in order to recognize an impending catastrophic failure, such as a large magnitude earthquake. And then we also saw these phases of delocalization or non-monotonic localization. And so less than half of the experiments experienced maximum localization immediately preceding failure. And then the maximum strain localization on average occurs at 90% of the failure stress. And so this is what we call non-monotonic localization. And this phenomenon is observed in the crust in Southern California. Oops, here it is. And so in this analysis by Yehuda Ben Zion and Ilya Zaliapin, they did the exact same type of statistical analysis that we did. In fact, we used their analysis in our work, which came after their work, where they divide up this Southern California into these series of squares, and then they calculate the proportion of the area occupied by the low magnitude seismicity throughout several decades, in fact. And so preceding these 3 earthquakes, for example, in Southern California. And so in general, we can see this general localization with time, but in fact, it's also at times non-monotonic. So preceding the Hector mine earthquake in particular, there's this phase of delocalization where the strain the low magnitude seismicity rather, began to delocalize, and then the earthquake happened. And so that's similar to what we saw in the laboratory. And so the next question we asked is, what conditions promote these phases of delocalization? And so the next work that built on this examined 2 parameters. So in the title, we can see we looked at the confining pressure and then the amount of pre-existing damage in the rocks. And in this case, these are experiments on westerly granite. And so in these granite rocks, we create pre-existing damage by heating them. And then these figures, this direction is towards macroscopic failure, so with the differential stress increasing. And so here you can see the range of confining stresses and also fluid pressures we're able to introduce in the laboratory. And so in this case, we slightly changed the way that we're quantifying localization, because in our new method, we remove some of the choice of the parameters required in the other method. So in this case, we identify the high strains similar to the previous way I showed you, but then instead of adding this grid in order to count the occupied volume, we create a polyhedron around the high strain magnitudes and then calculate the volume of that shape. And so when it's larger, and this shows an example earlier in loading, the high strains are more delocalized, and when it's smaller, then they become localized. And in this experiment, you can see this localization happening before failure. So this is earlier in loading and later in loading. And then we examine this localization of these three different strain components again. And so what we saw in this case, in terms of what conditions promote delocalization, when we have experiments with the larger confining pressure, we have this greater localization of the high strain events. And this is really consistent with what we observe in the field, which are includes these type of flower structures that develop along strike slip faults. So this much more highly localized at depth, where there's higher confining stress, and then delocalized at the surface, where there's this lower confining stress. And it's also consistent with the fracture geometries that we've been able to observe in the lab at experiments performed at lower confining stress and higher confining stress. So at lower stress, we have more often these arrays of fractures with a predominantly vertical trend. But then at higher confining stress, we tend to see more localized structures that are favorable for shear. And so then the next factor that seemed to promote delocalization in these experiments is that the experiments that had greater pre-existing amounts of damage promote delocalization. And this makes some sense if we consider this just this simple schematic drawing where you have a relatively intact rock and you only have a few fractures or flaws from which to grow, then perhaps you're more likely to have one fracture that grows at the expense of all the other ones. And maybe some of them grow a little bit, but in general, you stay growing one throughout loading. But when you have a more heavily damaged rock and there's this more flaws distributed throughout the rock, you have a greater chance that these smaller fractures can begin to propagate and so promote these phases of delocalization. And this is consistent with previous X-ray tomography experiments that did some nice work also with heat-treated granite and saw that the amount of pre-existing damage in the rock also controls the type of failure transition that the fractures in the rock experience going towards failure. And in this work, we also saw that the dilative strain experiences more systematic localization than the shear strain. And so this provides another piece of evidence that we may want to focus on the dilation in the crust rather than the shear strain in order to recognize this onset of the precursory phase. And so building on this idea of is it dilative strain or shear strain or tensile failure or shear failure that's controlling the deformation behavior of rocks? So I've just focused on the strain calculations that we can do in the lab, but of course we can also identify the fractures with the X-ray tomography data in 4 dimensions. And so in fracture mechanics, there are some well-defined rules about the orientation of fractures relative to the maximum compression direction and how that relates to whether the fractures are expected to be dominated by tensile or extensile deformation or mode 1 failure or shear failure. And so based on previous experiments in which you have to do this type of laborious unloading that I mentioned earlier, we have this general idea that the deformation of crystalline low porosity rocks in the upper crust is dominated by this mode 1 failure of fractures oriented parallel to sigma 1. But then after the peak failure stress, the way that the rock macroscopically fails is by this through-growing shear fault. So the question is, how do you go from extensile fractures to a through-going shear fault? And so we were able to look at the data from the experiments to understand if this, first of all, is actually the case. And what we see is an opposite trend to what others have claimed. And so first, we saw this dominance of shear fractures earlier in loading. And then later, the extensile fractures become dominant, at least preceding the macroscopic failure stress of the rock. And so then we used boundary element method simulations to understand why this transition was happening, because it was so surprising. And so what these models suggest is that it can occur because the growth of the fractures, so first of all, the formation of shear fractures, and then later the propagation of extensile fractures optimizes the global mechanical energy of the system. And so this once again gives another point towards tracking the dilative strain, because this is the type of deformation that's dominating the rock preceding macroscopic failure. And so now I keep talking about which one may be more useful to track, but actually we've used machine learning to predict the distance to failure. So to actually predict what I'm talking about, potentially predicting in the experiments. And so this early work, we used these type of decision tree machine learning models to predict how close the rock is to failure. And we have these 6 different rock types that we did this prediction with. And then with machine learning, we don't allow it to be a black box, and we actually examine which features are used in the predictions of these systems. So we can look at the features that contain information about the contraction, dilation, and shear strain, and we see that the models tend to rely on the dilation to make their predictions. So once again, something more for the dilative strain. And then we also saw with the different type of statistics that we used to characterize the strain field that it's the mean of the dilative strain within a local area that helps provide the best prediction. So better than the extreme values, like the very high values of the shear strain, for example. But then the situation becomes more complex when we consider systems unlike our laboratory setup, in which there's a nominally intact rock without macroscopic faults. So in this case, we use 3D discrete element method simulations in which we can put in these macroscopic faults with an array of different types of geometries, because we expected that that the fault geometry should control the type of strain that develops around them. And so this movie is showing an evolution of one of these models in which we're shearing the top and bottom boundaries, and then the fractures are growing. So in this case, the bonds are breaking between particles, and first the pre-existing faults form, and then later the new faults are growing. And so with the models, we predict the timing of fault reactivation and then the timing of macroscopic failure in these models. And so we did this. These models are cheaper than experiments at ESRF. So we did this with a lot of different type of models with the different geometries I showed you, as well as different normal stresses which represent this depth within the crust. And so what we saw is that independent of the fault geometry that we use, the predictions depend on the same set of characteristics. So those are the features that I'm showing here, and this is showing how the models are using these features. And so near the fault, the predictions depend generally on the velocity parallel to the shear direction. And they also depend on the shear strain. components of the strain field and not the volumetric components. So that's different than what we saw in the laboratory, of course. And so now I'll conclude. And so I want to highlight again that these experiments at ESRF are just so integral to my work, and it's one of the only way to observe directly the deformation of rock that's happening in the upper crust in 4 dimensions on ID19 and BM18. And the only way I can use this data in my work is depending on the hard work of the people that work at ESRF, including Ben. And so I'm so grateful for all of you who work there and spend all of your time there. And so to answer the questions that I asked at the beginning, how does this deformation evolve preceding earthquakes? So deformation localizes, but it's not monotonic. That's similar to seismicity in Southern California. This delocalization is favored in rocks with more pre-existing damage and at lower confining pressure. In which geophysical properties could be the most useful to track in the crust? So on intact rocks without a through-going fault, it seems to be the dilative strain. And when we have these segmented fault networks in the DEM models, then it's the shear strain. And so in the future, we want to include in the experiments these type of macroscopic faults, as well as another aspect of the earthquake cycle, which is so important to the predicting the timing of earthquakes, which is how rocks heal in the interseismic period. And so this really requires long time scales in the lab, and we hope to be able to do this with this BAG project that's proposed and has been spearheaded in a large part by Ben Cordonnier, and that's called Chronos. And so we hope that we'll be able to study such processes in the future. Thank you.